Hi everyone, my name is Taojiannan. I'm a PhD student at the University of North Carolina and Charlotte. In this presentation, I'm going to introduce our paper, MutualNet, Adaptive ConvNet via Mutual Learning from Network Width and Resolution. So, deep neural networks have achieved great success in different areas. However, traditional neural networks are only executable at a specific resource constraint. For example, MobileNet V2 can only run at 300 milliflops with 3.5 million parameters. However, if we want to do inference using a smaller MobileNet with fewer network depths and widths, we have to retrain the model. But in real applications, the resource constraints are changing with time by many conditions. For example, when the battery is high, we may have enough computing capacity for the full model. But when the battery is low, we only have limited computing capacities, so we have to switch to a smaller model. A simple solution to this problem is to keep several models in the device and switch among them. And this will consume large memory footprints and is not scalable to many different constraints. To address this issue, we need an adaptive model which is executable at different constraints. Previous works like SNet and USNet proposed to sample subnetworks by the network weights during training. The trained model can run at different network weights, with the performance drops dramatically when the flops constraint goes very low. We note that the computational cost is determined by both the network scale and input scale. Only focusing on the network scale cannot achieve the optimal accuracy efficiency trade-off. To achieve better trade-offs, we propose to balance between network scale and input scale. Besides, different scaled images contain different semantic information. So we propose a mutual learning framework to learn multi-scale representations from different network scale and input scale. This is an example to illustrate our method. In each training iteration, we sample 4 subnetworks by the network weights. The largest one, which is the full network, the smallest one, which is 0.25 in this case, and 2 random ones. We always feed the largest resolution to the full network because the largest resolution contains the richest semantic information. The other subnetworks are fed with randomly selected resolutions. Note that the full network is supervised by the ground truth label using cross-entropy loss, while other subnetworks are supervised by the full network using KL divergence loss. The total loss is the sum of full network loss and subnetwork loss. We explain that this learning scheme allows each subnetwork to learn multi-scale representations from both network scale and input scale. This is a simple example with only 2 subnetworks and 2 resolutions. Subnetwork 0.4 is trained with resolution 128, and subnetwork 0.8 is trained with resolution 192. During backpropagation, their gradients are accumulated and are used to update the weights. So, as shown in the figure, because subnetwork 0.4 shares its weights with the subnetwork 0.8, the gradients of subnetwork 0.4 consist of 2 parts. The first part is derived by itself with no resolution 128. The other part is derived by subnetwork 0.8 with large resolution 192. We note that this allows the subnetwork 0.4 to leverage the knowledge embedded in larger subnetworks and larger resolutions. Due to the random sampling strategy in training, Every subnetwork can learn such multi-scale representations from both network scale and input scale. After training, our model is executable at different width resolution configuration. Note that one width resolution configuration corresponds to a certain flops constraint. So we tested the performance of different width resolution configurations. This table shows the results of MutualNet V1. Here, we sample the network width by a step of 0.05. But if you want to have a more fine-grained table, you can sample the width by a smaller step. After we get this table, we choose the best performing configuration under each flops constraint. And this makes up our query table as shown at the bottom. For deployment, we only need to keep the model weights and the query table. The size of the query table is negligible. So the memory footprint of MutualNet is the same as a single model. During inference, when given a resource constraint, we can look up the best width resolution configuration in the query table and adjust the model accordingly. We conduct the experiments on MutualNet V1 and MutualNet V2 backbone. We show that MutualNet outperforms USNet over the whole flops spectrum, especially when the flops is low. We see that on MutualNet V1, when the flops goes to 21 million flops, MutualNet significantly outperforms USNet by 16 points. We also show that MutualNet outperforms independently trained models under the same width resolution configuration. Even this configuration is not the best configuration MutualNet found at that constraint. This illustrates that the multi-scale representation can benefit all configurations. We further show the benefits of mutual learning scheme by comparing with EfficientNet. EfficientNet also highlights the importance of balancing between network scale and input scale. However, in EfficientNet, different model configurations are considered independently. EfficientNet trains different model configurations individually and chooses the best performed one at a certain constraint. While MutualNet trains different model configurations in a unified framework, where different configurations can transfer their knowledge to each other. So MutualNet significantly outperforms the best model configuration in EfficientNet. We also explain that MutualNet is different from multi-scale data augmentation from the view of gradient flow. In multi-scale data augmentation, different scale images are used in different iterations, but in one iteration, the gradients are still optimized towards a single resolution direction, while in MutualNet, the gradients are optimized towards a mixed resolution direction in each iteration. The difference becomes more distinct when more subnetworks are involved. We also show that MutualNet is well generalized to object detection and instance segmentation. MutualNet clearly outperforms USNet and independently trained network. The visual results show that MutualNet is robust to different scale objects. Another interesting finding is that as we increase the width lower bound, the adaptive range gets narrower, but the overall performance is improved, especially for the full network. The results are shown in the left figure. Inspired by this, we increase the width lower bound and apply MutualNet to boost a single network. The results show that MutualNet outperforms popular data augmentation and regionalization methods on different datasets and backbones. So MutualNet is also promising to serve as a training strategy to improve the performance of a single network. Codes have been released on GitHub. Thanks for your interest.